Yes. You cannot, yes. The way that you do that is by having, so you can have, let's say, a delay on each link, okay? And then you can say for every traffic from K to L, the sum of the delays along this path cannot be more than, it can be no more than whatever your threshold is. So that will be more delays. That means make the problem much harder. So then we get to Pareto optimality. So that's so so that's harder to do. So you can do you know, it is everything is possible. I'm sorry. Well, not everything, but yes, but most of the things are possible. Yes, no, you're right. I mean, we can do that. We can have multi-criteria optimization. The other thing that is possible as well is to have a weighted function. You can say, I want to minimize the costs, and that carries 50% of importance, so 0.5, and then the other 50% is in terms of the amount of delay. Okay, but typically properties like delay and delay especially, you don't want to minimize it. Okay, and you know what happens is that in a network like this, if you minimize the total delay, okay, that means for some flows it may be very little, but then for other flows may be high. Okay, so typically for delay is not part of the objective function that you want to minimize, it's part of the constraint. It says my delay should not be more than that for any flow. And so then you guarantee that all your flows, right, okay, so then it's not a point of minimization, it becomes a constraint. It will be an additional constraint here, or an additional set of constraints there that say for all the flows that the delay cannot be more than that, right? Yes. And then you can do, I mean, as I said, this is, you know, I mean, if you look at the literature, there are probably thousands of papers that have formulations that are variants of this. Every network problem is going to be different. I'm not trying to say that all the problems are exactly like this. There will be exactly like this in terms of these multi-commodity flow constraints. Okay, these will always be there because you have the flow conservation. Anything you carry in the network will have to obey the flow conservation. Beyond that, the objective function can be very different. The other constraints can be very different. You want to take delay into account, you can do that. You know, you can, and you want to take energy efficiency, you can do that as well. You know, there's all sorts of things. Correct. Correct, yes. Right, so I guess that's similar to the question that came from the other student, yes. So here's the thing. When I say I want to minimize, so I have the traffic, right? So the traffic is known, it's input to me, okay? And then I have the cost, and I say I want to minimize the cost. Basically, this is a routing problem in a sense, right? Route my traffic over the links such that the cost is minimized. The problem with what you're saying is, okay, I have to have something as an input, and if the traffic matrix is not an input, that's a problem, right? Because how am I going to set up a problem if I don't have the traffic as an input? However, what many in this sense of maximizing carried traffic, which is really what you are looking for, the way that you start is as follows. You start with the traffic metrics again. Sorry, so you start with the traffic metrics, okay? Let me see. Yeah, so this is the traffic metrics, right? You start with that, and then you say, you put a factor lambda in front of it, and then you say, okay, minimize the costs. but at the same time find the largest value of lambda for which your cost is under this. Okay, and now what this means is that you maximize the carried traffic because you maximize this factor lambda, which tells you how much more traffic than the matrix that you gave me. Okay, because otherwise it will be difficult to apportion the traffic to the KL pairs, right? So I'm not, I mean, I haven't seen any problems like this, but I have seen it in the variant that I described, where the traffic matrix is given, but then you try to maximize a constant factor lambda that tells you how much more traffic you can put under this cost. Does that make sense? Yeah. The traffic? Yes. Yeah. It's no, it's this BKL. That's the given traffic. Okay, and no, the BKL. Okay, yeah, you see that? Yeah, this is part of the input. Yes, and so this is taken into account here because this says that the total traffic that will have to be sourced is BKL, and the total traffic that will have to be synced will also be BKL. So you're guaranteed that you're gonna transmit all your traffic. Yeah, the point is not shown there. You're right. So yes. So this, huh? With the mouse? Ah, okay. Yeah. Okay, I can do the mouse. Yes. So. Right. So if I go back, okay, this BKL gives you the input amount of traffic from node K to node L, and then this is also taken into account in the constraints because in this multi-commodity flow, this says that if I is K, in other words, if I is the source, it has to source BKL amount of traffic. And then the second one says if I is L, where I is the destination, the sink, it has to sync BKL amounts of traffic, so all the traffic will be sent and received. Yes? Correct, yeah. Okay, I may have something in the, so let me see if there's anything else here. No, I think that's the end of the presentation of this one, okay? And so now I'm going to talk about a specific problem, okay? So this is my next talk here. Okay. Huh? It's on this computer. So I can give you the power. Yes. I can give you a copy. I have a USB. I can give it to Dr. Yad, and then he can distribute all the. I don't. Yeah. Yes. All right. So. So this is the problem that we have worked on, and the reason Dr. Yad asked me to present this is because we have a KAU project that we hope to extend this for a much more difficult problem than the one that I'm going to describe. So, all right. So this is the routing and wavelength assignment problem in rings. Okay, and so I'm going to talk about the routing and wavelength assignment problem. I'm going to talk about existing formulations, not our work, previous work. Then I'm going to talk about our formulation that uses maximal independent sets. So remember I asked you a question about independent sets earlier, right? The reason was that it is related to this particular decomposition. I also talked to you about, asked you about vertex cover, which is also related to this. Okay, so if we talk about optical networks, right, there the medium obviously is optical transmission over particular wavelengths, right? So So we have a light path, and a light path, an optical connection is also called a light path, and a light path is basically a physical path and an associated wavelength. Okay, so there's a path and a wavelength over which the connection is carried. Okay, there are two variants. There's the online problem. Online problem is when the network is in operation that says, okay, yeah, the connection comes in, I have to decide how to route it, and sometimes I don't have sufficient resources, and then I block that request. Okay, and then there's the offline problem in which I have a set of static demands, and then I need to establish them. So this is a network design problem. The static RWA is a network design problem like the ones that I have been discussing. Okay. So I'm going to look at the offline version, the static version first. So my input is the network topology graph, okay, and a traffic demand matrix. And the matrix is how many light paths. So TSD is the number of light paths that need to be established from source S to destination D. Okay, that's all. And of course, it has to be at least one, and could be any number. It's obviously an integer. Okay. What I'm going to talk about is this version, the min RWA version. There's this max RWA version that is not really, it's actually related to your question. So the max RWA says maximize the demands established for a given number of lambdas, okay? Somewhat similar to what you said, but I'm going to look at the one that is most interest to network operators. So the network operators say, this is my forecast demand for the next 2 years. How do I build a network with the least amount of resources to satisfy that demand, right? And so this is, I'm going to satisfy all the demands with the minimum number of lambdas or wavelengths, because a lambda actually costs a lot of money, okay, so for operators. So there are two constraints, wavelength continuity that says a light path must use the same wavelength along its path. Okay, so if I'm working on the blue wavelength, it has to be the blue wavelength until the destination. Okay, and then the other one is the distinct wavelength constraints that says if two connections are using the same link, well, you have to assign them different wavelengths. Okay, so it's not difficult to see that both variants are NP-hard for any topology except for chains. So if you have a path network, just a path network, then the problem is polynomial. But if you turn the path network into a ring, the problem becomes NP-hard. Okay, so and it's NP-hard for any other topology. It's NP-hard for trees, actually. Okay. It's NP-hard for stars. Even for star networks, it's a hard problem. Okay. So here's an example, right? So I have a connection from 1 to 6, and it is on the blue wavelength, and the blue wavelength is used throughout. Okay. And I have another one from 1 to 4, and this can also use the blue wavelength because they doesn't intersect with the other one. Okay. Here, okay. Here what I have is I have 3 connections sharing the same link, and they have to have different wavelengths. Okay, so this is a lower bound on the number of wavelengths, because obviously if I have n connections that are using the link, then I have to have n distinct light paths. It's a lower bound, not an optimal solution. The optimal solution may in fact be larger than that. Okay. So, did you notice the difference? Here's what I'm going to do. I'm going to give you the same solution, slightly different. So you can see the same number of light paths. Okay. What did I do? I just changed the order of colors. Same connections, different order of colors. So what does that mean? This is actually a very important property of these problems, which is the symmetry. It says that this solution is optimal, this solution is optimal. Okay? In other words, if I just use a permutation of wavelengths, of colors, right, I get the same solution. You and I know that. We understand about the symmetry. The solver does not. What this means is the solver will find the solution. and will then continue the branch and bounds until it finds this solution, and continue the branch and bound until it finds another permutation and another permutation that are all equivalent, but does not know that, so it doesn't stop. Which means that this solution or this solution may be part of a very large number of permutations that have the exact objective value, the exact same objective value. And so how many are these? Can be up to k factorial, where k is the number of wavelengths in the solution, right? And if k is large, that means you may have millions or billions of permutations that have the exact same objective value, but the solver does not know that, continues to evaluate all of them, and does not have a criterion to stop. And so the symmetry problem, it's not unique to optical networks or with this particular problem. It actually arises in many other problems, makes the solution much harder, much more time consuming, because it's not an easy way for the branch and bound technique to stop and eliminate all those k factorial equivalent solutions. Okay. All right. So there are three different formulations of the problem, which two of which I have already discussed, the arc link and the path link formulations. Okay, so let's look at this one. So in this case, this is the link type formulation. And so you say, okay, from I to j, I have a variable Cijlw. Okay, so Cijlw says is there a light path from I to j, that uses link L on wavelength W. Okay, and so this is a 0-1 variable. It either does or it doesn't. Okay, so that's the solution. So, and then basically what you do is you have a formulation very similar to the one that I showed you, only instead of the Xijkl, you have these Cijlw variables. Okay. All right. This is the path formulation that I explained, and Dr. Yad suggested I have an example, and this is an example. Here you say, okay, instead of considering all possible links, because L here can be a large number, right? Can be up to n squared, where n is the number of nodes, and so I have a lot of variables like this. What I can do is I can create k paths between I and j, and restrict my light paths to go over these paths only. So now what I need to have is this type of variables, Cij and 2 refers to the path W. And so now instead of using n square of this, L links, I can use only k, and k is typically a small number, like 3, 4 maybe, okay? You don't have any more than that. And so you say, is there a wavelength from I to j on the second path on wavelength W? Okay, so this is a much more scalable formulation, but again, it's not as encompassing as this one, because this will consider all possible paths. And there's an exponential number of possible paths between I and j. This one only considers k paths. Okay. Yeah, maybe 3 or 4. K will be 3 or 4. That's typically. Okay, right. You will find the optimal solution for this selection of paths. Okay? So this is what I'm saying. You qualify that. So I'm finding the optimal solution for these paths. The paths here are input to the problem. Here the paths are not input. The paths are decided by the problem. So if you look at this will be the absolute optimal. Okay. This may not be as good as the previous one, but for practical purposes, we have found that this is quite good. Okay. But strictly speaking, this is not optimal. It is only optimal within for this set of paths that you give me as input. Does that make sense? Typically it's shortest paths, right? So think about it this way, right? So, you know, right, because think about it this way. Imagine the US, right? And so you want to have on the eastern coast, I live in North Carolina, which is on the eastern coast, and let's say I want to have a light path to New York, which is also on the eastern coast, right? So typically, I'm going to get a path that goes along the east coast to New York. I'm not going to take a path that takes me from North Carolina to Louisiana to Texas to California to Washington State, you know, to North Dakota, to Boston, and then down to New York, right? Because I'm going to be wasting a lot of resources. So typically, these paths are selected on the basis of length. And sometimes, depending on the requirements, you may also think about disjoint paths, okay? Especially if you are looking at, you know, okay, so you're trying the shortest paths that are also disjoint. These are correct. These are computed offline, and they're input to the problem, yes. Mm-hmm. You mean for this formulation? Yes. Number K here. No, K is a number of paths. Has not. Right, right. But first of all, in a small network like this, you may not even have 5 disjoint paths. I mean, you probably have 5 paths, but right. No, my point is that typically K is much less than n minus 1. Yeah. All right. And so, and now you can set up a formulation kind of similar, but now your variables are in terms of the paths as opposed to the links. Okay. You've seen this before. I explained it. Okay. The reason I'm showing it here again is because now you can use it to remember how we color, right? We color them, okay? We basically find a vertex cover, okay? Now here's the problem. Can I set up a formulation to do this? And the answer is yes. And the formulation is based on maximal independent set. So let's look at this, okay? So this is a solution, right? This solution says 1 will be green and 6 will be green because they don't intersect. 2, 3, and 5, 2, 3, and 5 will this magenta color because they don't intersect. And 4 is going to be a different color, okay? Because it intersects with 3 and intersects with 1, so it can have the same color, okay? How can we express this mathematically? We can express that mathematically by looking at independent sets, okay? Independent sets is a set of vertices, no 2 of which are adjacent, okay? Now I have the notion of the maximal independent set, which is an independent set that is not a subset of any other independent set. Okay, so what are the independent sets here? 1 and 6 is an independent set, okay? 1 and 5 is an independent set. 2, 3, 6 is an independent set. 2, 3, 5 is an independent set. And 2, 4, 5 is an independent set. Okay? Yes? No, there is here there is no maximum, so this is a maximal. The difference, maximum means in terms of a range. It's a maximum number in a range. Maximal has a different meaning here, which means that it's not a subset of a bigger set. Okay, so the notion here is different. Does that make sense? It means there is no bigger independent set that has this other one as. So, in other words, 6 is an independent set by itself, but it's not a maximal independent set because 1, 6 encompasses as a subset, right? I'm not interested in 6 because that will not give me the minimum number of colors. I'm interested in, in this independent set, I know that I can color this and this the same color because they're far away. They're not adjacent, right? Okay, so let's look at this solution, okay? 1, 6, same color. 2, 3, 5, same color. 4, same color. So how do I express that mathematically? 1, 6, so I take this independent set, then 2, 3, 5, 2, 3, 5, 2, 3, 5, that's another independent set, and then I have to have 4, so I can take this independent set where 4 belongs. So what this tells me is that if I enumerate the independent sets and I create a variable for each independent set, then I can set up a formulation that tells me, do I take this independent set? Do I take this independent set? Do I take this independent set, right? And so the variables will be 0, 1, and if I take this independent set, then that means these two light paths, 1 and 6, will be one color, okay, because they have to be the same one. Then the solution says 2, 3, and 5, this will be another color, and then it will say, okay, this is the other independent set, 2, 4, and 5. I don't need to color 2 and 5 again because I don't need to, but I'm going to give 1 to 4. Okay, so now that's the nice thing about this formulation, is that enumerate it's a very different than the other ones, right? It says just enumerate the independent set, the maximal independent sets, set up x variables for them that are 0, 1, and then set it up so that it will tell you which ones you're going to get in the final solution, and that minimizes the number of wavelengths. That's it. Does that make sense? So this is really the step. You pre-compute the k paths. It's the same as before. You pre-compute the paths because, remember, this one you require to have the path in order to set up the path graph, right? So you have the paths, you create the path graph. So this is the pre-compute the paths, create the path graph. Each node in the path graph is a path in the original network, and two nodes are connected, have an edge in the path graph if the paths share a link. Okay. Then enumerate the maximal independent sets of the path graph and set up the ILP to assign the wavelengths to its MIS. Okay. And so, for instance, if you have two light paths, so if I go here, if you have two light paths from this node to that node, then the formulation is not going to be a 0, 1, it's going to be an integer. It's going to say take this MIS 2 times. Okay, and because you have two light paths of 1. All right. So that's basically how it works. Okay. Here's the interesting thing about this particular work. Okay. Or this particular formulation. Here. This one gives you as output the maximal independent sets. It doesn't tell you what color to color them. So therefore, the symmetry problem goes completely away. It just says 1 and 6 can be colored the same color. 2, 3, and 5 can be colored the same color, and 4 can be colored a different color. Then all you need to know is which ones can be assigned the same color and how many colors to use, right? And then you can just say color 1, color 2, color 3, color k, however many colors you have. So the symmetry problem that the other formulations have does not appear here, right? So if you look at the variables and constraints, the size of the formulation, okay? Link 1 is n to the 4th times w, okay? And the number of constraints n cubed times w. The path is much more compact. It's n squared w, okay? But these have the symmetry problem, and this is reflected by the fact that w is part of the constraints and variables. Okay, MIS does not contain w. Okay, the number of constraints is n cube n square, but here's the problem. The number of MISs on a general graph increases exponentially with the size of the graph. Okay, that's the problem with this formulation. So what can we do? All right. So let me show you. We did this work a few years ago because we were studying the problem of energy efficiency using grooming in optical networks. So I had my students, they set up the formulation, and I said, okay, let's run it on a small network to make sure that everything is okay, and then we can try larger networks. So he ran it on a 6-node network, and we got all the results really good. We're getting 80% better energy efficiency by doing this particular grooming method. And then I said, okay, can you run it now on the NSF network that has 14 nodes? So he goes back, crunches the numbers, and he says, okay, if to do the 14-node network, we probably need another month to get all the results back. And I say, why? And he told me the numbers, basically went over this and said, this is how much I need for 6 nodes, and 14 nodes, it goes exponentially. And so we were actually looking at this formulation that time, okay? So I said, there must be a problem. Let's back up. Let's not look at the grooming, which is a more difficult problem. Let's look at the RWA, which is a sub-problem of grooming. If we can make that faster, maybe we can work with the grooming as well. So we ran a few, so we looked at RWA, and so here's the results that we get. This is Simplex 11, so a few years ago. Now Simplex 12 is faster, machines are faster, so the results are probably a bit better than this, but the relative difference actually is probably in our favor. Okay, so let's see what happens. This is ring networks, okay, ring networks only, and this is the number of nodes in a ring, and this is the amount of time it takes you to find the solution for its formulation. And down here I'm going to tell you what formulation it is, okay? So for a link formulation, so this is exponential, so this is logarithmic scale, 0.01 second, 0.1, 1 second, 10, 100, 1000. The limit is 2 hours, okay? So we said, okay, because we're going to run a lot of instances, and these are actually averages of about 30 instances each, and we have to do many algorithms and many ring sizes. We said if it takes more than 2 hours to solve, okay, I don't know how long it's going to take. So we basically plot this here. It says it ran, more than 2 hours. Now, obviously, if I were to extend it, it will be exponential, right? It's not going to be constant. I don't know how long, okay? I just did not run it, okay? And the other thing is here, for some instances, we ran out of memory. And so if we ran out of memory, we couldn't even run the instance. And so we were going to record it here, okay? So link formulation, this is saying that up to 10 node rings, I can solve it within 2 hours. But then for 12 node rings, I don't know how it's going to take. I mean, I can extrapolate from that, but I don't want to do that, okay? What about the path formulation? The path formulation, remember, is much more compact, okay? And so you can see that immediately. I can solve 16 nodes up to 2 hours. Beyond 16 nodes, it's above the limit, okay? Now here's the interesting thing. For ring networks, the link and path formulations are equivalent. Why? Because in a ring you only have 2 choices. You can either go clockwise or you can go counterclockwise. So using the link does not gain you any advantage in terms of optimality. All right. Okay, what happens with the MIS formulation? With the MIS formulation, you get something like that. You get really fast immediately. Okay, because you don't have symmetry problem, it's much smaller. But the problem is that the size of the formulation grows so quickly that at 12 nodes, it doesn't fit into the memory. And then you may say, well, double the memory. Well, but if I go up by 1, my memory doubles. So even if I double the memory in my machine, I will only be able to solve an instance with n+1 nodes, right? Because it also grows exponentially. So we looked at this and said, okay, obviously 2 hours for 16 nodes is too much. Can we do any better than that? And there's a reason for the 16 nodes, because SONET networks have a maximum size of 16. Okay, so if we can solve 16 node ring networks very quickly, that's all we need to do. So there is no way that you can improve the path formulation. So we looked at this one. This looks very promising, right? The problem is the size. If we can do something better with the size, then maybe we can improve that. So that's where the decomposition part comes into play. So here's the thing, okay? The very first observation is very simple. This is saying that, look, in a ring, I have clockwise paths, the red ones, and counterclockwise paths, the green ones. But none of the green links intersect with any green paths intersect with any of the red paths. What does that mean? It means that if you construct a path graph, as we said before, it will be two parts. It will be one graph here, another graph that has no edges with the other ones, basically two paths, okay? So the path graph is the union of two disconnected graphs, the clockwise and the counterclockwise. CW is clockwise, CCW counterclockwise, okay? So if I want to express the maximal independent sets on the overall graph, all I have to do is take one maximal independent set of one graph and a maximal independent set of the other graph, right? And so I don't need to enumerate the MISs of this graph. All I have to do is enumerate the MISs of the two smaller graphs, which actually 1/2 the size. And because they are 1/2 the size, each of them is the number of MISs is the square root of the number in the original graph. Now, instead of having to enumerate capital M MISs, all I have to enumerate is square root of M. And because of the symmetry, this set and that set are the same, so I don't really have to enumerate twice. I only have to enumerate one of them. So the number of variables here that is orders of magnitude less. Okay. So let me show you what this means. Okay. So this is what I showed you before in terms of the running time. If I do this very first decomposition, this is what I get. Okay? What I get is that for 16 nodes, I can do it in 100 seconds. That's almost 2 orders of magnitude than the path, the best other formulation. And so it's even faster than this one, okay? Even initially, so you can see 3 orders of magnitude here difference. Okay. So what happens is you get these 3 orders of magnitude, but then because of the size increasing, that's why the gap closes. Okay, so can we do anything better even for that? So the answer is that we can. And then, so this is the very first decomposition. Then the other step you can see is the following. Take the ring and cut it in half. Okay. Now, you have 2 sets of paths. You have the paths that only use these links and the paths that use only these links. These are independent, so you can decompose them again before. And then you have paths that use both sets of links, okay? So to create, so you can express the path graph of the clockwise as 0, this part, 1, this part, and then this third path over there, okay? So what this does is further cutting down on the maximal independences that you have to evaluate, because to get the maximal independences of this whole graph, you get the maximal independences for these paths only, which is the same as this path because it's symmetric, okay? And then you have to add something to account those paths, okay? And so basically the MISs will look like this: a 0th part, a 1 part, and then what we call the core group, which I'm going to skip the details, but basically accounts for these other paths. Okay. So the number of MIS variables goes down, the number of constraints goes up, but the trade-off is not linear. In other words, for MIS variables goes down by an order of magnitude, the number of constraints goes up by a few thousand. Okay, so that's the trade-off is to our favor up to a point. Of course, after a point, it doesn't make sense, so we'll get to that. Then you can recursively do that. So you cut it in half, then you can cut it in quarters, and then look at, obviously for a large ring, right? If you have 16 nodes, then you have 4 nodes at each quarter, and you do exactly the same thing. It just changes the formulation a little bit. So here's what happens to the variables, okay? This is why the problem runs out of memory right away. So for 10 nodes, you have 1 million variables. For 12 nodes, when it runs out of you have more than 10 million. You have about 20 million variables, okay? When you do the first decomposition, you cut that to the square root. So if you look at this line, the red line is the square root of that line because it goes down by that, okay? Then you do the first decomposition to half the ring, it goes down even further, and then quarters, it goes down even further. If you cut to eighths, it doesn't, for 16 nodes, which we are interested in, does not make sense to have only 2 nodes at each part of the ring. Of course, if you go to larger ring sizes, which in terms of practical interest, it's not of practical interest, but if they were, you know, obviously you would see a much better improvement there, so you would be able to do further decompositions. But since we are only interested in 16 nodes, okay, we stop there. Okay, so now here's the results. This is the first decomposition. The second decomposition is this one, and the third one is this one. Okay. So, you know, the third one doesn't pay off at 16, but it does pay off, let's say, 24. You can solve it. The other one goes under 2 hours, right? And so here what happens is that I can solve 16 node rings at 3 or 4 seconds. Before, if you were to use any of the other 2 formulations, so the link one is, you know, 7200 seconds, right? So that's 3 orders of magnitude less than we can do compared to the path formulation. And of course, we're not even discussing the link formulation. Will take days. Okay, so that's the that's really the result here that we have. So, yeah. Yes. Yes. Yes, it is, because remember, this is the path graph. It tells you that if you want to go from 1 to 2, you have 2 ways of going from 1 to 2. You can either go there, or you can go the other way, which is actually reflected on this. Okay. Now, my point is that the path. So if now, the traffic pattern doesn't have, so if I have an instance of the problem, it will depend on the traffic pattern. So one traffic pattern, one traffic matrix as input may give me traffic from 1 to 2. The other one may not give me may not have traffic from 1 to 2. So the problem instances will differ in terms of their traffic metrics. But in terms of computing, that's the other nice thing about this approach, is that the path graph, okay, does not depend on the traffic metrics, because this is a ring, right? So you have there's only 2 possibilities. You either go from 1 to 2 this way, or you go the other way. So I can pre-compute the MISs. I can store them. So if you give me another instance, I can just use the MISs that I have, and then based on the traffic pattern will tell me whether to take an MIS or not. So the MIS is indeed something that is independent of the traffic pattern. Does that make sense? Thank you. So that concludes my presentation. And so the point I'm going to just make is that we are looking at a different problem in optical networks, which is elastic demands, where you don't. So here the granularity of traffic allocation is 1 wavelength, right? So you either, you know, if you have traffic from 1 to 2, you have to give it a whole wavelength. But this may be wasteful of resources, so there's a new development called elastic optical networks, where you can actually give them, give the traffic a specified amount of spectrum, not necessarily a full wavelength. So the same problem arises. It's more difficult, because instead of granularity of 1 wavelength, now you may have granularity of down to 1 slot, and the slot, you know, you can get 1 slot, 2 slots, 5 slots, or whatever for your traffic. So the question is, the problem that we are looking at is, can we extend this to work in the case of demands that are more granular than finer granularity than a wavelength? Simplex, we use simplex, yes. No, it's not a simulator. So we don't build a simulation model for this. Okay, I see what you're saying. So, like, are you thinking about OpNet, for example, where you give it a graph and then traffic demands, and you say simulate that? It's somewhat similar. So what we basically I'll go back to this, I guess. So basically what we do, I don't have the formulation here, but if you remember from my other formulation where I had the, let me bring this up. Yeah, so I have to. Yeah, okay, so this is, so let's say I had this formulation, right? So the way that you specify to simplex is you define the variables xi, j, k, l, and then you write down all the constraints, and you write down this formula, and you give it, if there's 100,000 constraints, you have to give it basically what you give it is a matrix, okay? The matrix is the number of, on one side is the number of variables, so we may have 1 million variables, and on the other side is the number of constraints. And so what this is, each row corresponds to a constraint like this, and then you have the appropriate coefficient for those variables that appear in that constraint. Okay, so yes, basically you have to write a Java program or a Python program, whatever, to generate this huge matrix, which then you give it to simplex, and then simplex will take care of everything. Will do the branch and bound that I mentioned. Any domain that you can formulate it like this, absolutely. Simplex is widely used, yes, yes. Mm-hmm. Thank you.
شطر الطالبات في أحد لسه باقي؟ I think they need the slide. We can share it. I'll take it later from you.